Welcome back to Braun Engineering. My name's Alan. In this video, we're going to be using the APSX Nano Swiss Lathe to make its own tool holders. Making square parts on a lathe is always a good time. We'll teach you how to do it. So here's the tool holder. It's made out of 6061 aluminum. It measures 12 millimeter across the flats. It has a pocket to suit a PH Horn S274 series insert, some relief contours on the front of the part, and then 3 tap drill size holes for the mounting screw for the insert, as well as the mounting screws to the machine. So we'll get started in Fusion 360, walk you through the programming, take you out to the shop, give you some footage of the part being made, and then address some concerns that came up along the way. Before we begin, I'd like to give a huge shout out to our friends over at GWS Tool Group for sending us this 3/16 3-flute end mill that we use to make this part. Thank you so much, Taylor and Avalon. Great seeing you at West Tech. If you're unfamiliar with West Tech, it's a convention that happens here in Long Beach, California once a year in the fall. Hopefully we'll see you there next year. Everybody else, stay tuned and enjoy. Taking a look at our model here in Fusion 360. This CAD came from APSX. They make it available for download on their website. If you do a search for Nano Swiss OD tool holder, they do sell these on the website if you want to purchase one, but they also list the CAD file for download and you can get it there. I made some modifications to the model. The first one is that I made this corner relief for the back edge of the insert larger. And the reason I did that is because I want to use the largest end mill possible to avoid deflection when especially putting this contour onto the front of the part. So I used a 3/16 end mill and I just tweaked the model until I could squeeze a 3/16 end mill through this gap. So as you can see here, it's 0.196 between those faces, so that'll clear that end mill nicely. After that, I just drew one construction line onto the part, and I'll show you why that's important in a moment. Let's pop over to the manufacturing suite. The general strategy I used to make this part was I divided the part in two, and that's why I put that line there. And I did some turning and milling to both halves of the part. So we're going to use the OD lathe tooling to reduce the diameter of the stock, and then we're going to use the live tools to create all the features. The stock we're using is 3/4 inch, and as you can see, that fits that 12 millimeter square tool holder in there nicely. So our roughing and our finishing cycles that we used on the lathe tooling, I'm not going to cover that in this video. I talked at length about that in my previous video, so go ahead and check that out if you haven't already. But we will simulate kind of the process here. So our roughing cycle, removing as much stock as we can as quickly as you can, coming in to create a nice finish with the finish pass. This finish diameter is slightly smaller than the 12 millimeter square. In fact, you can kind of see the edge of the part poking out right there. Now, the reason I did that is it pre-edge breaks those edges and puts a nice radius on there so you don't have to come back and deburr it later. Now, once we have all that turning work finished, we're going to come in and do our milling. So first things first, we are going to mill the flats. And the way we did that is bringing the tool to about 1 millimeter step over, which is 15% of the diameter, just kind of the happy climb milling space. We're always going to be climb milling to keep a consistent cutting force on the part. And we're going to be rapiding back out to the front of the part and then proceeding in again. So it's kind of like an adaptive clearing pass. And I found this to work really, really well in almost all situations. So one thing to note that as you mill this, the stock gets thicker towards the center of the flat and the cuts become heavier and heavier. And that heavy cut right in the middle of the part is sort of the limiting factor for your feeds and speeds. So what I found worked really well for this part was running at 8,000 RPM and a feed rate of 30 inches per minute. And so you can kind of use the vibration of the machine and the sound of the end mill to gauge if you're pushing too hard or if you can go a little bit faster. And this ended up working out pretty nicely. We're going to use the pattern function in Fusion to put that flat on all four sides. And then once that's done, we're going to come in and do the front contour at the end of the part. So we did 2 step downs here to remove the stock, and then 1 spring pass. And then after that, we just came in for 1 finish pass. And I believe I left 10 thousandths on the edge of the part. Actually, that would be back in here. Let me take a look. Yeah, so we did a step down of the full diameter of the end mill. And then we left 5 thousandths radial stock on the end. So that finish pass is only a 5 thousandths depth of cut. This is a pretty long cut for this diameter end mill, so we wanted to just keep the stock removal small. Now once the contour is on the end of the part, we're going to come in with an adaptive cycle to clear out that pocket. Again, we'll be using similar speeds and feeds to what we were doing for the facing operation, so 8,000. We're going to cut that cutting feed rate down to 3 inches per minute, but we are going to keep the same amount of load, so just about 1 millimeter, 15% of the diameter of the part. We're not going to leave any stock anywhere, just because we're going to come in with 1 cleanup pass, and it was unnecessary to leave any. One thing to note, when you see in the video, the cut gets really heavy here around this hole. So I think what happened is when I selected the geometry for this, I didn't select this hole, I just selected this face. And I guess Fusion 360 doesn't recognize that stock is still there, so it's going to cut heavier around that hole. So just something to watch out for, learn from my mistakes. Okay, once we have that pocket milled out, we're going to drop in there with the drill. Spinning that drill at 5,000 RPM with a plunge feed rate of 4.5 inches per minute. This actually is kind of aggressive. If you watch the video, I think there's a couple frames where you'll see the spindle stall. And that also has a lot to do with the lack of lubrication that the drill is getting, so the chips aren't clearing the flutes. They're getting kind of a frictional lock happening. I think that was really the main problem. If this was flood coolant or oil, I don't think we'd experience that problem. We're doing 29 thousandths pecking depth, and we're going to clear all the way through the hole just so we don't have a burr at the bottom. And then from there we're going to do the same thing, but we're going to clear out the 1/4-20 tapped hole, and then we're going to drop in there with the end mill, and we're going to helical mill that hole to size, and that should be number 7 drill size, which I think is 0.201 inch. This helix, to avoid deflection, I kept things very tight, and we're only doing a 3-degree ramp. Let's see, same RPM, doing a feed rate of 5 inches per minute. So that's all the features complete on the first half of the part. Now we're just going to do essentially the same thing on the back half, although it's a bit simpler. So again, we'll come in here and clear out the stock. And then we're going to do our flat milling. Now I used that one line I drew just as a reference, and I'm overcutting the back of the part just to make sure that we get no burrs or anything on the back. Let me skip ahead. From there, after that, we're going to pilot drill that hole, and again, helical mill it to size. And then after that, we're going to come in with our parting blade and part this guy off. And I got a little lazy here. I decided to actually part it at the interrupted cut just to keep the size of the part. That's actually not important at all for this part. It could be an 1/8 inch or even a 1/4 inch longer. It's not really going to affect anything. Part of me just wanted to see what would happen trying to part off a square and to see if the Nano Swiss could actually handle it. So asking it to go through an interrupted cut was just a good opportunity to see how rigid the machine is and what you can get away with. So I wouldn't recommend doing it, but hopefully it will make for some fun video to watch. It did get through the cut, is the good news, but I again wouldn't recommend doing this when you go to make your part. I'm spinning the spindle at 800 RPM. We're doing a cutting feed rate of 0.5 inches per minute. After that, I just have a couple pass-through codes. This is just a wait code, and then sort of a cycle restart prep for the next cycle code. I discussed that in my last video. That's totally optional if you want to use those. All right, so let's go out to this shop, make some chips. Thanks for hanging in there. So let's pause here for a moment to address two important things. The first is, yes, I did get a haircut. Thank you for noticing. Second thing is we are going to stop between milling the front half of the part and milling the second half of the part. And the reason why is because when I went to run this program the first time, turned the front half, milled the front half, turned the second half, and when I went to mill the flats on the second half, I noticed right before it took its first pass that the front flats were at about a 45-degree angle. So as that end mill came down, it wasn't going to blend the flat surface of the front half with the back surface, or back half. It turns out the Nano Swiss switches between M102, which is turning mode, and M101, which is the indexing mode. When you switch between those two, like we're doing between the first and second half, it will lose its C index, 0 reference point. It's poof, gone as soon as you switch. So I brought this to the attention of APSX. They told me that it was due to a programming limitation in Linux CNC, which is the base software that the Nano runs on. For this part, the way I did it was I paused the program between the first and second half, and then I eyeballed my C0, the top of the part, the flat. I eyeballed that in, and then continued running the program. And that actually worked pretty well. You can see that it's a decent blend. You can't really feel any burrs or ridges, and I was, reliably able to do that across 3 parts for the filming of this video. So if you're just making tool holders to make tool holders to use on your machine, you'll be able to reliably do that, no problem, I think. If you are using the machine for customer orders for production, this is a major limitation that you need to be aware of. I'm not bringing this up to admonish APSX. I'm actually bringing it up because I'm hoping someone out there watching this video is skilled on Linux CNC and can help fix the issue. So please, if you have any ideas how to go about correcting this, throw them down in the comments. I'd love to have a conversation with you. Okay, let's take a biscuit break and hop back onto the machine and finish this part. Thank you. Meow, you're so cute. Good girl. Okay, so closing thoughts on making these tool holders. If you are making these, at this point you will need to tap the 1/4-20 mounting holes, and I believe it's a 3.5 millimeter for the insert screw. I'm not actually planning on using these, so I didn't justify the expense of buying taps to do it with. If you had a third tool, live tool on the machine, you could thread mill them. That'd be really cool. And then also maybe there's a way to program in thread milling once the part's complete. I'm going to leave that up to your guys' creativity. Just be aware, if you notice from the helical milling on these parts, those 1/4-20 mounting holes are egg-shaped. They are not round. So I brought that up with APSX, asking them if they could help me out. They said that I needed to adjust the backlash between the Z and the Y axes on the machine. I haven't done that yet. They sent me a link on how to do it. Maybe I'll make a video showing you guys how to do that once I get around to it. But until then, thank you so much for enjoying this video with me. Please like and subscribe, and I'll see you on the next one. Cheers.